We look at the world around us every single day, but have you ever really stopped to think about the invisible rules that make it all work? Today, we're going to pull back the curtain on the amazing science of light, shadows, and reflections. So let's just start with a little thought experiment. Picture this. You walk into a room. No windows, no lights anywhere. You shut the door, and boom, you're in complete and total darkness. What do you see? The answer is so simple. But it's also kind of profound. You see, absolutely nothing. Now that might sound obvious, but that one little fact is the key to understanding everything else we're about to talk about.
And right there, that's our foundation. Light isn't just helpful for seeing, it's the main ingredient for sight itself. Without it, the world is just a blank canvas. So where does this essential ingredient even come from?
Well, basically everything falls into two big groups. On the left, you've got your luminous objects. Think of them as the rock stars of the light world, like the sun or a flashlight. They produce their own light. Then on the right, you've got non-luminous objects, which is pretty much everything else, right? A chair, a shoe. The only reason we can see them is that light from one of those luminous sources hits them and then bounces into our eyes. Okay, so if light is always zipping around us, what happens when something gets in its way? This brings us to the really cool and mysterious world of shadows. Now, to really get how shadows work, you gotta look at how different materials treat light. Some are transparent, meaning light just sails right through them. That's why you can see perfectly through a clean window. Others are opaque, like a brick wall. Light hits them and bam, full stop. Nothing is getting through that. And then, of course, you've got the stuff in the middle, translucent. Think about frosted glass or maybe some tracing paper. Light gets through, but it gets all scattered and jumbled up, which is why you see blurry shapes but no clear details. All right, so keeping all that in mind, we can finally ask the big question. What exactly is a shadow? It's actually a super simple recipe with just 3 ingredients. First, you need a source of light. Second, you need an opaque object to get in that light's way. And third, you need a screen, like the ground or a wall, for that patch of darkness to actually show up on. If you miss any one of those 3, you get no shadow. Simple as that. Now, this is where shadows get a little weird. They have some really interesting properties. For instance, have you ever noticed that a bright red car still casts a dark, colorless shadow? That's because a shadow is just the absence of light. It doesn't have any color of its own. They can also totally fool us, like when we make shadow puppets, and their size and shape can stretch and warp like crazy depending on the light's angle. So we've seen how blocking light makes a shadow, but what if we could actually control that light with a little more precision? What if we could use these exact same principles to build something amazing, like say a camera, using just a simple cardboard box? This is such a classic experiment. All you do is take 2 boxes, one that fits right inside the other. In the bigger box, you poke one tiny little pinhole. On the smaller box, you make a little screen out of tracing paper. Then you just slide them together, point that tiny hole at something bright, and take a look inside. And when you finally look at the image that shows up on that little tracing paper screen, well, you are in for a real shock. The image is completely upside down. Seriously, the top of the tree you're looking at appears at the bottom of your screen, and the bottom appears at the top. But why? What in the world is going on? The answer is coming, I promise. But first, there's one more piece to this puzzle. All right, so we've seen light get blocked to make a shadow. Now let's look at what happens when light is bounced back perfectly. Welcome to the world of mirrors and reflections. You see, a reflection isn't an absence of light like a shadow is. A reflection is light. It's just been sent in a totally new, predictable direction. A mirror's surface is so smooth, it's like a perfect trampoline for light, bouncing it right off without scrambling any of the information it carries. And this just spells out the difference so clearly. A shadow? It's a fuzzy, dark, colorless patch. But a reflection? That's a sharp, clear image that shows all the original colors and details. They really couldn't be more different. Okay, let's just recap for a second. We've got dark patches on the ground, we've got upside-down images inside a box, and we've got perfect copies in a mirror. These things seem totally unrelated, don't they? But it turns out they are all governed by one single, incredibly elegant rule. One of the characters from our source material, Paheli, was totally on the right track. She started thinking, wait a minute, all this stuff we're seeing, Maybe it's only possible if light moves in a straight path. And a super simple experiment proves this beautifully. Look at a candle flame through a straight pipe. Yep, you can see it no problem. But the instant you try to look through a bent pipe, the flame is gone. It disappears. The light just can't make the turn. And that's it. That's the unifying theory. Light travels in a straight line. That's why an opaque object casts a really clear shadow. And it is the secret behind the pinhole camera. Light rays from the top of an object travel in a straight line through the hole to the bottom of the screen, while rays from the bottom travel to the top, and that's what flips the image. So the big takeaway here is this. One simple, elegant rule that light travels in a straight line is the master key. It unlocks our understanding of shadows, reflections, and the fundamental principles that make every camera and telescope ever built actually work. And that leaves us with one last thing to chew on. We've established that shadows are colorless because they're just an absence of normal white light. But what would happen if the light source itself wasn't white? What kind of shadow would you get from a bright red or a deep blue light? Something to think about.